In this video I want to balance out a combustion reaction. Gasoline burning, that is a combustion reaction. The compound octane has this particular molecular formula. We will not be doing nomenclature of those on our test. So like what you would be given would be the molecular formula of the compound. And then one thing you need to appreciate and to know is that this organic compound is going to react only with oxygen and is going to produce carbon dioxide and water. Now the phases here, we put gases here. Oxygen's also a gas. The hydrocarbon just depends on its molecular weight. Gasoline, as we know, is a liquid. And then what we want to do is we want to tweak the front end of these amounts so that the equation is balanced. We're basically working with the law of conservation of matter. Whatever mass, whatever number of atoms we start with, we have to wind up with the same number. Because currently we see that's not the case. If I go in and I take inventory of the atoms on my reactant side, I have 8, 18, and 2 for carbon, hydrogen, and oxygen. That's different than what I have for carbon, hydrogen, and oxygen on the product side. 1 carbon, there's 2 hydrogens here, and then for oxygen, there's 2, 3 oxygens. So now I need to change these in front so that everything's balanced out. Now notice one thing that I did here is that I did oxygen last, and that's pretty typical for a combustion reaction. There's a general rule or rule of thumb that we use when we're balancing these equations. If we have elements in their elemental form, free elements is the phrase that you hear oftentimes. Those elements are balanced last. And again, when we say free elements, we're talking elemental forms. So the diatomics, monatomic metals, etc. These few little rules that you see given for balancing equations are like really helpful hints. One of the most important things they do is they just make your work easier when you're balancing equations. Okay, let's balance this equation. So first off, carbon, 8 here, 1 here. Well, since carbon is only showing up there, what I can do is put a coefficient of 8 in front of the carbon dioxide molecule. And these molar coefficients here, they are multipliers of the elements that are in the formula. Now notice, I cannot do, this is a no-no. So if I start with CO2, right, that's carbon dioxide. I can't go in here and put an 8 as a subscript because there's only 1 carbon in that compound. So that's why we're only changing the coefficient in front. So please don't start changing subscripts once you have the molecular formulas in place. Hydrogen, there's 18, there's 2. Well, what's the math? Right, 2 times 9 is 18. What does that 9 represent? The 9 represents that molar coefficient. And now look what happened. So this change, that change affected oxygen in both examples. That's one reason why we do oxygen last. We know in combustion reactions, it's going to be messed with multiple places. We might as well wait till the very end to deal with it. That's kind of the logic of that phrase, balance free elements last. Okay, so it's no longer 3. What we have, that's 2 times, well, let's just write it out. 2 times 8 coming from the CO2, 1 times 9 coming from the water, the oxygen in the water molecule, and that's equal to 25 oxygen atoms now here. Now, when you do a combustion reaction, half of the examples produces an even number of oxygen atoms, and then half of the examples produce an odd number of oxygen atoms once you get to the last step. If it's an odd number of oxygen atoms, bear with me, let's take a look at this in a strange kind of way. Let's kind of apply the same logic with oxygen, like over here, with what I did like with the hydrogen and even the carbon. You know, think about this. So 2 times what number equals 25? Now, obviously, it's not a single whole number, okay? But there is a fraction that we can use here. 25 halves, if you will, times 2. Right? What happens mathematically? The 2 cancels out, and now I got 25 here. What is that? That is my multiplier. That represented molar coefficient, 25 halves. Now, on one level, this is not an incorrect statement here. It's just not complete. We don't leave it as a fraction here. But it certainly balances the atoms. Like I said, this is not necessarily an incorrect statement. It's just an incomplete statement. What I want to do in the last step is I want to get rid of that half there. And the way I do that is I multiply this entire expression by 2. So 2 times 1, 2. 2 times 25 halves, 25. Now I get rid of my fraction. Now I have a whole number here. 2 times 8, that's 16. 2 times 9, and that's 18. Do you have to do it this way? No. Is it convenient? Yes, I think. This little technique of using a half in certain places can be very useful in balancing equations, especially dealing with diatomics. And that's it for this problem.